Okay, so we're going to take a look at the old exam 13 here, the multiple choice questions. So problem number one, a delta G value equal to 0 kilojoules per mole means at equilibrium. So if delta G is equal to 0, that means there's no driving force. And so that means it is at equilibrium. There's no driving force for forward reaction or reverse reaction. And so that means that Q is equal to K, basically. But K, what does K mean? K doesn't always mean that we have 1 bar, 1 molar. Gases will be at 1 bar, solutions will be at 1 molar. That's not necessarily one. These are what we call standard thermodynamic conditions. In standard thermodynamic conditions, there could be a driving force because of the reaction. Gases will be at 1 bar and solutions will be at 1 molar. This is standard. Temperatures will be at 298. That's not standard, but that's the most common temperature. Or K at 298 Kelvin is equal to 1. Now, what would this be? Well, let's take a look here at another scenario for this particular problem. And that is, what if I ask you the same problem except I said delta G under standard conditions? Yeah. Well, actually, let's take a look at this one again. If we have delta G value equal to 0, this is equal to delta G under standard conditions plus RT ln of K. And we don't know what we are. If we were to solve this, okay, so if delta G under non-standard conditions is equal to 0, then this simplifies into delta G naught is equal to minus RT ln of K. And the K is equal to E to the minus delta G naught over RT. Okay, so it depends on, if we're starting off at standard conditions, what is the driving force? If we're starting off at standard conditions.
Question.
Uh-huh.
Why did the RT turn negative when you moved the delta G naught over?
Well, I just I set this equal to 0 and then subtracted RT ln K from both sides.
Oh, okay.
That's how it is. And so the way to think about this is, if we were to start at under standard conditions, is there a driving force? That is, under standard conditions, K is equal to 1. For Q, under standard conditions, we should say Q. Q is equal to 1. But that's not necessarily at equilibrium. And so this would be the driving force. If we're under standard conditions, is there a driving force for forward reaction or reverse reaction? There's driving force for forward reaction would be negative, and reverse reaction would be positive. And so we don't know what the equilibrium constant will be. However, what if we had something like this? Instead of delta G equal to 0, what if we had delta G naught equal to 0? If delta G naught is equal to 0, that means under standard conditions, there's no driving force. And so that means if there's no driving force under standard conditions, then K must be equal to 1. Well, how often do you get a K equal to 1? Well, everything has to be 1s. In other words, the products all must equal 1, and the reactants all must equal 1. Basically, if under standard conditions we're at equilibrium. So this is saying that under standard conditions we're at equilibrium. And so if this were instead of delta G, which is non-standard, if this instead were delta G naught, so delta G naught value equal to 0 kilojoules, what does that mean? Well, that means that you have a very weird situation where K, the equilibrium constant, is equal to 1. If that's the case, then what would be true? Well, A wouldn't be true because we don't know what the temperature is. So if this said delta G naught, A may or may not be true. B would be true because, gases would be at 1 bar, which is standard, and solutions would be at 1 molar if they're gases and solutions. Well, we don't know what it is. And C would be true. Well, C actually is not true because we don't know if it's 298 because delta G naught doesn't require the temperature to be 298. And so only B would be true. So this is the advantage of doing these. You do these multiple times. When you do these multiple times, then you know the basic. When you know the basic, then you try to push it, a little bit. It's like when you're doing something that's routine, and then all of a sudden you try to make it fancier or something like that. And this is the same kind of thinking here. You've gone through this. Okay, now what can I do? Well, what if I change this, or what if I change that? What would it do? So if this were delta G under standard conditions, then B would be correct. If this is just delta G, then D would be correct. Two, which species has a higher standard entropy, SF4 gas or SF6 gas? Well, we predict, and this is what I said on the answer key. And this is something that you don't have to. You don't have to. I mean, you would think, for example, here, the more complex the gas this is a pattern that we can see. So SF4 is seesaw structure. SF6 is octahedral. So, based on the number of atoms, you would think that SF6 would have higher entropy, and so that's what I picked. I picked SF6 earlier because it has more atoms, and the more atoms, there would be more positions. But in reality, this is one of those things. We see a pattern in the trend. We can see this pattern in the trend. Let's take a look at some of the data from Appendix D here. And look at, see, nitrogen. So this is an example they give in the book, which is nitrogen, NO. NO is 210, N2O is 219. So we have more atoms there. This is nitric oxide, this is dinitrogen monoxide. 3 atoms. You'd expect there to be higher entropy because there would be more waves right in that. Take a look at some other nitrogen species here. NO2, the 240, 3 atoms. Now N2O4, 6 atoms in that molecule, 304. And so this is a higher entropy here. That's gas. And then we go to liquid. Liquids are obviously going to have lower entropy than gases. And so we would expect SF6 to have higher entropy because it has more atoms, SF4 to have lower entropy because it's fewer atoms. But maybe based on the shape and the types of vibrations, SF4, since it has a kind of asymmetric shape to it, might have more vibrational modes, we call them, than something like SF6. And so that could account for it, but that's beyond the scope of the class, when you're looking at vibrational vibrational modes. And this is something you do in advanced chemistry. Is you would look at vibrational modes. We can take a look at some vibrational modes of like water. Water has this kind of asymmetric kind of shape in a way. It does have some symmetry. Vibrational modes of water. And so we can see how things vibrate here. So this is one of the vibrations of water. Actually, there are only 3 vibrational modes of water. And so there are only 3 ways. This is the second way water can vibrate. And then there's a third way, which you'll see shortly, I think. Or maybe we won't see that. This is the third way. Yeah. So there are 3 ways water can vibrate. That's based on the shape of it. And so the same thing happens with something like this. There's probably more complex vibrational modes for something like this because of its asymmetry versus this with that symmetry. So that's probably what accounts for it. But on the test, I don't expect you to know, but sometimes you have to worry about the actual data. So on this particular problem, I didn't mark off when I graded this last year, but based on what we know on the trends that we observe, we would say SF6 has a higher entropy. But when you look at the actual data, it conflicts. So this is a key I made up from last year. When I went through this with Zoom, I just selected B. We'd expect B. Yeah, they're pretty close though. 3, and most likely it's due to vibrational modes, but you don't expect it to know. We can actually calculate the number of vibrational modes using math. Math is called group theory. 3, absolute entropies are determined from first law. First law of thermodynamics just says that energy is neither created nor destroyed. Energy is conserved. And so energy content of the universe is fixed. The first law of thermodynamics. The second law of thermodynamics is the driving force. The entropy of the universe increases with a favorable reaction. And in other words, there are 2 ways of thinking about this. One is just delta S in the universe. Delta S in the universe should go up. But when we do our calculations, delta S of the universe is too much. So if we look at the system, then we look at what we call the positional entropy. There are 2 types of entropy that we look at. Positional entropy, which is delta S. Delta S, this is why I'm thinking SF6 has a higher entropy because there are more positions that 6 atoms can have versus 5 atoms here. So this is 6, 7 atoms altogether. 5 atoms altogether here. So there are more positions. But then when we throw in vibrations, the vibrations restrict the positions. And so there are probably more vibrational modes here. That's probably what accounts for it. But they're all positional entropies. Even with vibrations just change the position of where the atoms are. So we have a positional entropy, and then we also have energy entropy. And so delta H, if it's exothermic, then we're going from chemical potential energy, which is very well ordered, to heat. And heat is very disordered. And so exothermic reactions will increase the entropy by converting chemical potential energy, which is low entropy, to heat, which is higher entropy. So that's the second law. But we need the third law of thermodynamics to determine absolute entropy, because we need an absolute zero. What's the absolute zero of entropy? That's the third law. The absolute zero of entropy is the perfect crystal at 0 Kelvin. That will give us. And then heat and heat capacity is related, because the more ways that the molecule can absorb. The more vibrational modes there are, the more ways it can absorb energy. Oddly enough, when you heat a pot of water, not all the energy is absorbed. Just the energy that corresponds to the vibrational and rotational modes of water. This is why microwaves are so efficient. Because microwaves, what you do is you tune the energy so it does one specific thing, rather than dumping in a whole bunch. Because when you look at the absorption spectrum for water, there are 3 peaks. And so if you're using just heat from a stovetop and it's heating the entire spectrum, only 3 of those will be absorbed. Three regions of heat will be absorbed, and the rest will just be transmitted. But anyway, this is what we had for entropy. And this is why we can get the absolute entropies. And this is why when we did the previous calculation, where we're looking at delta G of the reaction, we got delta G's of formation of the products, delta G's of formation. When we're looking at delta H of the reaction, we think delta H of formation of the products minus delta H of formation of the reactants. But when we do the entropy, it's the absolute entropy. It's the absolute entropy because we have an absolute 0. Except for the cations and the anions. The cations and anions will have an arbitrary 0. So the third law doesn't apply to cations and anions. So these are the things. When you do these problems a lot, then you try to make connections and you try to branch out, and that way you're better prepared for the test. Because if you can think of these in different contexts and different scenarios, then you're going to be better prepared in general for stuff that comes along. Which reaction below is spontaneous at high temperature but not at low temperature? Okay, high temperature means it's an entropy favored reaction. The higher the temperature, that means that delta S has got to be positive, because if delta S is positive, we want to make that more favorable. But not at low temperature. Not at low temperature means it's kind of endothermic in that case. So let's take a look at the first reaction. The first reaction we'd expect to be endothermic. Calcium carbonate is like limestone or marble. Marble might have some magnesium carbonate in there as well. Or travertine, or what else? Calcite. Calcium carbonate is like a stone. And to convert that into calcium oxide and CO2 gas is going to require a lot of heat. This is like heating rock up and watching it decompose. So this has got to be endothermic. If it's endothermic, it's not favorable. Exothermic increases the entropy of the universe. Endothermic doesn't. So in this case, that's not favorable. However, delta S, the positional entropy, is favorable because we're going to generate CO2 gas. There's going to be a lot more positions here. And so delta H is positive, which means it's not favorable. But delta S is positive too, which means it's favorable. So we just need to make the entropy term more favorable by increasing the temperature. And so this is favored at high temperature. So we have 4 scenarios. Are you familiar with the 4 scenarios?
I believe I wrote it down somewhere.
Yeah, the delta H, delta S, and delta G.
Yeah.
We have 4 scenarios.
It's on my whiteboard at home.
Okay, then you should be familiar with those 4 scenarios. Here, this is like a combustion reaction. We're combusting SO2 to SO3 using oxygen. So this is probably exothermic. But the entropy is going down here. And so when we look, we have 3 moles of gas going to 2 moles of gas. So if we increase the temperature, that makes this less favorable because delta S is negative. Here in this case, we're going from half a mole, so it's 1 mole of gas to 1 mole of gas. And so delta S doesn't really change much here. And so temperature is not going to have a big impact on this. This is most likely exothermic as well. It's a redox reaction. Iodine's a pretty decent oxidizer. Hydrogen's a great reducer, and we make hydrogen iodide gas, or hydroiodic acid. This one's exothermic. Strong acid plus strong base. It's exothermic, but as far as the entropy goes, not much is happening with the entropy here. So one that's going to be A. A is a very important reaction. About this time, I watched a documentary. You know what this is? is a kiln for converting calcium carbonate to calcium oxide for making concrete. And so this is a little historical thing. There's a Roman kiln. The Romans were experts at making concrete. Okay, 5. For the reaction of A plus B yields C plus D, the delta H is 450 kilojoules and delta S is 200 joules per Kelvin. The reaction under standard conditions is spontaneous at temperatures greater than 2250. Well, anyway, delta S is favorable, delta H is not favorable. And so, let's take a look.
Will you guys be able to plug that into the delta G equation?
Yeah. Delta G is equal to delta H minus T delta S. And so delta H is unfavorable by 450 kilojoules. And T, and then delta S this is unfavorable by 450 kilojoules, but this is favorable by 0.200 kilojoules per Kelvin. And so this is not enough to overcome this. And so we have to figure out what temperature will this overcome that. And so we set these equal to one another. And then once we set those equal to one another, then we can figure out what the temperature is. In other words, when we set it, we want this one to cancel out that one. If we want this one to cancel out that one, then we'll set this equal to 0. And then solve for the temperature. Temperature will be 450 kilojoules divided by 0.200 kilojoules per Kelvin. And that comes out to 2250. Okay. 2250 Kelvin. So temperatures greater than 2250 will make this whole thing negative. Temperature at 2250 will just make it 0. Oops, I forgot to put on this over here. I got an idea. I didn't realize this is flipped. I wonder on the video if it's not flipped. Or what? Okay. Yeah, it's got to be greater than 2250 because that's going to make this term more. And at 2250, it'll make this term minus 450. So we'll have positive 450 minus 450. That gets it. But we don't want it 0. We want it negative. So we need a temperature greater than 2250, which will make this bigger than minus 451. So if we get this to minus 451, then this 450 minus 451 gives us minus 1, which is spontaneous. And so that's why it's greater than 2250 in this particular case. Six. For H2O liquid to H2O gas at 100 degrees C in 2 atmospheres, select all the following quantities that are true. All right, this is kind of a trick one here because this is non-standard. 2 atmospheres is non-standard. But I'm asking you under standard conditions. So what we have to do is we have to say, okay, under standard conditions, what is it? That off for a minute. So under standard conditions, this would be, let's say, 1 atmosphere, 1 bar. So if we're at 100 degrees C, then water spontaneously boils at 100 degrees C. So if we were under standard conditions at this temperature, then we wouldn't be at 2 atmospheres, we'd be at 1 atmosphere, and then water would boil. If water is boiling, then this means it's at equilibrium. Liquid and gas phase are equilibrium, delta G naught would be 0. That is, we'd have boiling occur. Boiling is, you have that transition over. But we're not under standard conditions. So if we're not under standard conditions, boiling's not happening here. That is, delta G is not equal to 0 here. In fact, in this case, the reverse. At 2 atmospheres, this is not high enough temperature, and so it's not going to boil. And so delta G is going to be greater than 0 here. Higher temperature. So this delta G naught is like the speed limit. You know, what is the posted speed limit? Well, the posted speed limit is this, but we're not at the posted speed limit. We're at 2, not 1 atmosphere. And so when we're at 2, then this is the reality. Water doesn't boil at 100 degrees C with 2 atmospheres.
Oh, so that was not correct.
This is correct. This is correct. Let's say you're in a pressure cooker here. This would be a pressure cooker. The whole idea of pressure cookers is to increase the boiling point of water. So if we increase the boiling point of water, we can cook the food a lot faster in a pressure cooker. And so here, if we had something cooking at 2 atmospheres, you don't have to go that high, but if we had 2 atmospheres, then it's going to boil at a higher temperature. It's going to take more heat to boil that water. And this is not enough heat, so delta it's not boiling. Delta G is going to be greater than 0, which means it's not spontaneously boiling. But if you're in a pressure cooker, you might look outside and go, well, if I was not in this pressure cooker, what would water be boiling at? Well, if you're not inside the pressure cooker, then you'd be outside under standard conditions, and water would boil at its normal temperature, which would be 100 degrees C. And so this is just inside the pressure cooker, and this is looking outside the pressure cooker, what temperature water normally boils at. Yeah, delta G naught is standard conditions, and this doesn't apply to number 6.
Okay.
You know, this is non-standard conditions.
Right.
But this is saying, if this were under standard conditions at 100 degrees C, would it boil? Yes, it would boil. Well, it's kind of a weird question. Number 7 here. Let's see. KSP at 298 is 1.8 times 10 to the minus 10 for silver chloride. What is the KSP at 100 degrees C? So what we use is this equation. This is the Van Hoff equation. Lots of equations out there. This looks very similar to the Clausius-Clapeyron equation. The difference in Clausius-Clapeyron is K is equal to pressure in Clausius-Clapeyron. But anyway, so ln of K, the equilibrium constant at T2 divided by K at T1 is equal to minus delta H over R, 1 over T2 minus 1 over T1. You don't have to memorize this equation, but there are certain variants that you'd have to be able to figure it out. I'll just give you the basic equation, this equation, and figure it out. And so we plug in the numbers here. I give you delta H. You should know what R is, 8.3145. Joules, there's a unit mismatch here. You know, delta H is in kilojoules, R is in joules, so you got to convert one or the other. Then we solve for the temperature. And so, or the equilibrium constant. The equilibrium constant at 373 is 3.66 times 10 to the minus 8, which is this. So, in other words, at 100 degrees C, we expect more to dissolve.
At the end of that equation, is that K to the negative 1?
This one? Yeah. This is Kelvin. This is the temperature. Yeah. So this is kind of screwed up because this is the equilibrium constant. This is the Kelvin temperature here. And so But the kelvins will cancel out, the units cancel out here. So we're just left with this. And so it's more soluble at higher temperatures, the KSP increase. Take a look at the next one. Delta G naught. Okay, so this understanding conditions can be changed by altering what? Well, we can change the temperature. This is no standard temperature, but we cannot change the pressure because standard conditions require the pressure 1 bar for 1 atmosphere. And we cannot change the concentration.
Doesn't that have to be 1 mole?
It has to be 1 molar, and therefore, if it boils, then that's no longer delta G naught. So only temperature. Now, on the other hand, if this were delta G, not delta G naught, what could change it?
That would be ABS.
Yep, right. And so these are things you want to think about when you're going through these types of questions, extending it. 9, exothermic reactions lead to an increase in entropy. Actually, that's true because what we're doing is we're converting chemical potential energy into heat. Heat is a higher entropy form of energy. It's not as usable as chemical potential energy. And so that's true. That's the delta H. That's why we have this here. And so one way of thinking about this equation is delta G is going to be related to the delta H. Delta H is the energy entropy, and delta S is the positional entropy. Yeah. An increase in energy entropy is exothermic. 10. A 1 molar H plus aqueous at 298 Kelvin has 0 entropy. Well, this is true and false. So it depends on what people stated, because this is tricky. In the book it is. And so when you look at the book, it's 0, but when you think about entropy, in the third law, H plus 1 molar is not going to have 0 entropy. So this is false. It doesn't. It's arbitrarily defined as 0 entropy, but it does have entropy. And so that's what I was after there. It has entropy, but it's arbitrarily defined as 0 because you have 2 unknowns, 1 equation type problem. And so it's an arbitrary 0. We can see that on the chart. 11, K always increases with increasing temperature. We don't know that. It could decrease or increase. It depends. Because if we go back to Le Chalais' principle, increasing temperature favors the endothermic direction. The endothermic direction might be right or it might be left. We don't know. And therefore, it could go either way. And so this is false.
So it's not always, but if you
Sometimes, yeah.
It said can.
Yeah, it can, right. Right, that's true. Or if this were little k, the rate constant. The rate constant always increases with increasing temperature. That's true. If we look at this one, calcium carbonate plus 2H plus yields calcium ion plus CO2 plus H2O liquid. KEQ equals KC. Kc is the molar concentration. KEQ is what we call thermodynamic, or just K is the thermodynamic. Thermodynamic would be concentrations for aqueous and pressures for gas. Kc would be concentrations for aqueous and concentrations for gas. And so KEQ is not equal to Kc in this case, because KEQ would equal the concentration of calcium times the partial pressure of CO2 divided by the concentration of H plus squared. Whereas Kc would be the concentration of this number, the concentration of that divided by the concentration of this squared. Now, the concentration of these two are a bit trickier because are they in the same volume? They aren't, and so you have to do something different for that. So, okay, I guess that was the multiple choice. I think I did the other ones on the recording, the free response, and I think it's about time. I guess we're out of time. So I'll stop here.